By way of introduction, the idea behind this project is that it's really a kind of experimental project or a kind of search-based project, and the objective is to try and find out what kinds of things very, very simple rewrite systems do. It's the kind of work which really belongs to the kind of new science which Stephen Wolfram has been recently promoting. Basically, the idea is that it's well worth exploring what kinds of behaviour can be generated by very simple programs. The idea really is that in science we like to study various different kinds of pattern formation systems, things like differential equations or various different kinds of constraints or cellular automata. We like to study lots of different things, but usually what we do, especially regarding mathematics, is just to pick a few different systems sort of consciously and then study what they do. So, for example, people like to study the Schrödinger equation because that particular partial differential equation has relevance in quantum mechanics, but people will rarely pick a sort of random second-order differential equation and just start studying it. That seems like a kind of pointless activity. But one of the kind of points that Stephen Wolfram makes is that actually having a look at the dynamics of, say, randomly selected simple systems isn't pointless at all. It's actually very interesting and very rewarding. And so I took a similar kind of approach to string rewrite systems. For example, this picture here was generated using a very, very simple string rewrite system. And these are the kind of things I want to talk about today. So here's an illustration of the basic kind of system which I've been having a look at. We've got the rules at the top here, and this is the initial condition. And the basic idea is that we have this, what I'm going to call a string. You can also call it a word or a pattern. Basically, it's just a load of blocks of different colours. The idea is that we just keep updating this pattern over and over again according to these rules. So, how do these rules work? Well, basically, the idea is that we just scan this string from left to right, and we apply these rewrite rules wherever possible in a kind of non-overlapping way. So, for example, we start here and we apply this rewrite rule to the first block, and then we imagine our little writer or whatever it is going to here, and then it applies this rewrite rule here, replacing these two blue blocks with a red and a blue block, and then after the writer's done with these two, it moves along to the final two blocks and applies this rule again. So this is the this is the pattern on the next time step. And then basically that's all you need to know. We just keep applying the rules over and over again, and we see what kind of pattern emerges. You see here I've used these kind of little lines here to make it more explicit what kinds of rewrite operations are going on here. Okay, so really conceptually what I want to talk about isn't anything more complicated than this. It's just scanning the string and applying the rewrite rules where possible in a non-overlapping way. And all we're doing here is we're making a picture of the pattern which is produced in space and time. So you can think of this kind of left-right direction as space, and time is going downwards because we're showing the successive strings generated as successive rows reading downwards of this picture. So basically this is the kind of illustration, the kind of way I like to illustrate these kind of systems. I don't generally show these runners, which sort of indicate exactly how the rules work. Usually I just make these more sort of compressed space-time plots here. And basically all we're doing here is just showing how this string changes over time as we keep applying these rules over and over again. So these rules are the same as these, and this pattern is the same as this. It's just that I've omitted these runners showing exactly what's going on. Okay, so a fairly good question to ask then is, what kinds of behaviour can be generated by these different string rewrite systems? Well, the very simplest kind of non-trivial systems that you can consider are these ones where you just have two colours and you just have string rewrite rules which just involve length 1 or 2 strings. And so if you look through the space of all of those kinds of rules and look at what pattern they generate, that's a fairly easy thing to do, and you can quite quickly see by eye the different kinds of behaviour which are generated. For example, this rule here, this makes a fixed point in this case. So you can see that this pattern here, this string, is actually just fixed under these rewrite rules. And then you also have these rules which end up generating periodic orbits. For example, here, this thing just generates a period 2 orbit. Another kind of behaviour which you observe is this kind of linear growth. So this is something quite a lot rarer, but some of these rules do generate linear growth patterns. This one really seems quite simple. And then there's also another kind of behaviour that you sometimes see, which is exponential growth. So this can really occur because, according to our update rules, every little bit of the string is updated simultaneously. And so there are quite a few rules where the length of the string grows exponentially with time. And some of those end up generating some fairly rich nested or fractal patterns, like this one here. And so a fairly good question to ask is about complexity. How complex are the dynamics generated by these kind of rules? You see, the rules themselves are incredibly simple, and I think you'll agree that conceptually these systems are really very simple. And so traditional scientific opinion would probably suggest that the dynamics produced by these systems should be somehow correspondingly simple. Looking at this at the bottom right, we see quite a simple rule, and it looks like quite a complicated pattern has been produced from this initial condition, which just consists of a single red block. So this suggests that maybe this kind of intuition isn't correct. Maybe actually some of these very simple string rewrite systems can generate highly complex dynamics. Well, when one's interested in things like how much complexity can be generated, using a kind of statistical or automatic search-based approach isn't usually very successful. This is one of the lessons that Stephen Wolfram points out in his book A New Kind of Science. And in fact, a much better way to kind of study these kind of systems with potentially very complex behaviour is to try and just visualise what's going on. Well, visualisation's certainly something that's quite easy for these systems. I mean, it's really quite easy just to make these space-time plots, and we can just see in a second or so what kind of dynamics are being produced. So if we just have a look at all the different space-time plots of these different radius to two-colour rewrite rules, we can see what kind of complexity their dynamics have. And if one does that, one finds that the 131st rule out of that set of, I think it's about 258 rules, roughly anyway, the 131st rule, which is shown here, actually generates highly complex dynamics. So it's a very small rule. It just says replace every red block with a blue and a red block, replace every blue and red block with a red and blue block, and replace every pair of blue blocks with a single blue block. So if one just keeps applying these rules over and over again, then one can easily generate complex dynamics. In particular, if you just start with a load of red blocks and start updating this system, you'll see that the system enters into a really very high period orbit. So this is not one of those systems where the number of blocks grows very large. This system doesn't grow linearly or exponentially. Technically speaking, this system is periodic for a finite initial condition. But the thing is that the period is very high, and if you just consider how this system evolves, when you start with a lot of red blocks as the initial condition, the dynamics are actually very interesting. So here's the system running for a few hundred time steps, starting with just a load of red blocks as the initial condition. And you can see that there's some kind of regularity originally on the right. And if you look at the early elements in the string, they seem to be kind of oscillating between red and blue with pretty low periods. But if you look at what happens to pieces of the string which are further right, they're oscillating between red and blue with higher and higher periods. And pretty soon, it just looks like the behaviour is chaotic. Well, I analysed this rule a lot because it really stands out as one of the simplest systems I've ever found which generates highly complex behaviour. And in fact, I found that you can do a simple kind of substitution, and it really ends up kind of cleaning up the system and changing it into this thing shown on the right here. And what this is basically is a funny kind of cellular automata where the future state of a cell just depends on the current state of the cell and the current state of the cell to its left. So this has some special features that all the information is actually passed to the right within this rule here. And I analysed this rule a lot. I don't want this to be a mathematical talk, so I don't want to go through the maths of it very much. But I proved a very interesting fact about this rule on the right here. Okay, so if you have a look at this pattern on the right here, one of the interesting things about it is that if you let the thing run long enough, in a sense, any kind of information that you can think of gets generated. Let me try and be more precise about this. So, any information you can think of can be represented as a sufficiently long binary string. If you can encode any information you like as a binary string. So that's basically just a load of zeros and ones of some finite length. Well, it turns out that whatever binary string you have in mind, if you run this system for long enough, then you can select the row which is sufficiently kind of far down this space-time pattern on the right here. And if you then replace every black or dark grey block with a 0 and replace every white or light grey block with a 1, so effectively you're converting that row into a load of zeros and ones, then somewhere within that row you can find the data string which you thought of. So in other words, in a sense, the pattern produced by this rule is kind of arbitrarily complicated because it produces all possible initial conditions for itself. So this is a fairly interesting thing. I actually did quite a lot of mathematical analysis on this rule. Some of it can be found in the linked paper. Some of it I haven't actually published yet. It turns out to be a very interesting system. So this thing on the left here looks quite simple. And when you make this conversion to this cellular automata here on the right, it does have more colours and in some ways it does look more complicated, but it has some very nice relationships with things in group theory. Anyway, I don't want to get too sidetracked with the mathematics. I'm really interested in just telling you what kinds of behaviour were empirically observed. So, if one goes on to have a look at systems with 3 colours instead of 2, one almost immediately sees a huge variety of very interesting behaviour. For example, this space-time plot here, this was generated directly from a string rewrite system. The system grows linearly, but you can see that the system almost runs like a cellular automata. I mean, it has these little triangles inside it, which are certainly reminiscent of things like cellular automata rule 110. Here's another rule which has a very interesting pattern. I mean, the growth rate here doesn't look very smooth or predictable at all. And this is one of the kind of special features that string rewrite systems have, which is different to something that cellular automata have. Because in these kind of string rewrite systems, the number of cells can change quite dramatically, very quickly. And here, the number of cells is increasing and decreasing in a very kind of erratic way. And this entire pattern was generated just from starting with a single red cell at the top here, and just applying these very simple rewrite rules. And what's amazing here is how hard to predict the long-term dynamics seem to be. So this whole rule is just generated from this simple initial condition, and a good question to ask is, what kind of behaviour am I looking at here? Is this a rule which ends up growing approximately linearly? Does it end up going into some kind of periodic orbit or growing exponentially? What's going on here? Well, if you just make a space-time plot of the thing, like here, it doesn't seem to be clear what the long-term behaviour of this system is going to be. So run the system for longer. Here's the system run for 100,000 time steps, and you can see that it doesn't really look like the system settling into any kind of stable behaviour. I mean, is this system going to become periodic? Is it going to die out? Is it suddenly going to start growing exponentially? Even after we run the thing for 100,000 time steps, it's still not clear. In fact, I've run this rule for millions of time steps, and I still don't know what the long-term behaviour is going to be. The system looks too complicated to study mathematically, and I think this is one of those places where you really run into undecidability. I mean, Stephen Wolfram comments on this in A New Kind of Science, that when you have a look at the dynamics of some of these very simple programs, you quickly find these systems which have features which seem to be kind of undecidable. I mean, it could well be an impossible question to answer about what the sort of infinite time dynamics are of a system like this. Okay, so here's another example of one of these systems. Again, we're just running this thing from a single red cell, and we're just applying these very simple update rules again and again. And now we seem to have a kind of mixture of very complex looking dynamics and also some order here on the left. Here's another rule which seems to generate kind of linear growth, and this once again has a kind of mixture of complexity and order. Okay, so a good question to ask about these systems is just how complicated are they? Well, there's a pretty good kind of litmus test for whether one of these computational systems is truly complicated, and that's whether the system is capable of universal computation. What do I mean? I'm talking about whether a system is capable of emulating a universal Turing machine. So essentially, if a system's capable of emulating a universal Turing machine, that means that it can effectively be programmed to perform any computation. What that means is that if you pick your initial condition appropriately, the kind of space-time pattern which will be produced can compute the prime numbers or run Windows or do pretty much anything else which you have in mind. And so a good question to ask is, are any of these string rewrite systems universal? Do any of them have this property? Well, I suspect that quite a few of them probably do. Quite a few of these systems with complex behaviour are probably capable of universal computation. But proving that is notoriously hard because you have to effectively show that somehow you can use the initial space-time pattern as some kind of programming language and execute any kind of code that you want to. However, I was able to show that one of these kind of systems is computationally universal. So this rule here has 9 different colours, and in fact it's quite easy to prove that this is computationally universal. So I actually explicitly constructed this rule to show that there is a system with 9 colours which can do universal computation. And the proof is extremely simple because this system on the right, this is actually the smallest known universal Turing machine. This was proved to be universal just a couple of years ago now. And so this thing on the right is known to be a computationally universal system. And basically I set up this string rewrite system just so I could explicitly simulate this system here shown on the right. So this kind of page really proves that there are string rewrite systems with 9 colours that can achieve universal computation. Now, I'm almost sure that in fact there will be string rewrite systems with 3 colours which can do universal computation, maybe even with 2 colours, although proving that kind of thing can be extremely difficult. Well, okay then. So we know that there are systems which can achieve effectively any computation. We know that there are string rewrite systems which can effectively be programmed. But what about specific computational tasks? I mean, it's one thing to prove that a system's computationally universal, but as I heard Seth Bullock say, and it's a very valid point, really often the issue is not whether it's computationally universal. The issue is what kind of computations does a system naturally do? What kind of things is it good for? Well, it turns out that one thing that some of these systems are good for is arithmetic, because they can be used to do arithmetic in a kind of strange way which seems a bit unfamiliar at first. The basic idea is that some of these systems appear to have this feature that if we initiate them with a certain number of red blocks as the initial condition, then the thing will evolve and it will, make the pattern grow, and then the pattern will actually halt after some multiple of the initial number of blocks has been produced. And so, in effect, what these systems are doing is multiplication. For example, here, this rule shown at the top left here, if we initiate this with, say, 10 red blocks, then the pattern will evolve until we have a string of length 30, and then the system will halt. And so effectively, and that's actually true for any number of red blocks. If we start the thing with n red blocks, the thing will evolve until we have 3n blocks, and then the system will halt. So what's going on here? Well, basically, we can think of this system as multiplying by 3, because if we want to times a number by 3, all we have to do is evolve this system and wait until it gets to a fixed point, and then count how many blocks we have at the fixed point, and that'll be 3 times the number of red blocks in our input. And in a similar way, we can find other systems. I found these kind of things by doing automatic searches, and I haven't proved that these systems achieve multiplication, but I have checked that they do so for the first million or so initial for first 100,000 or so initial conditions. And so these systems at the top here, we have systems at times by 3, 4, 5, 6, and 7. And so there's something quite remarkable here. Because firstly, I think it's quite surprising that one can achieve a fairly sophisticated operation like multiplying by 7 using a very simple rule like this that doesn't really look like it has anything to do with arithmetic in a direct sense. But I think what's much more interesting is actually how this system achieves multiplication by 7. I mean, just look at the space-time pattern here. If you asked a human to make one of these string rewrite systems with this feature that, it grows until the thing's 7 times the input and then it halts, I would almost guarantee you that they wouldn't invent a system like this, because this system here seems to rely on kind of pseudo-randomness or complexity to achieve this goal of multiplying by 7. So this fact has two different spin-offs. Firstly, it makes the system in a way kind of difficult for us to rely on, because ultimately it's very hard to understand how this system achieves this multiplication by 7. But on the other hand, it also makes the system look very kind of creative. I mean, this system finds some way of multiplying by 7 which no human would have ever thought of before. And maybe it's even hard for us to understand exactly what's going on here. But nevertheless, this is the minimal string rewrite system which can multiply by 7. And so, in a way, this is showing us that often the kind of minimal rules which can achieve a certain task might do that in a way which is surprising to us and fairly complicated. Well, one can find rules that do many other kinds of arithmetic operations, like compute n mod 3, or check if the input number of red blocks has a particular form. We can also find 3-color rules which achieve multiplication by higher numbers, by 11. Although there's obviously a limit to what you can do. I would really like to find a rule that can do kind of universal arithmetic. Something like if you put in an initial condition of A red blocks followed by B blue blocks, then the system effectively computes A times B. But I haven't been able to find anything like that yet. But you can generate various different kinds of arithmetic operations, and it's quite surprising that you can do so. Okay, so there's a certain feature that some of these rules have, which I think lends itself to more kind of interesting applications, and that is reversibility. And so the thing is that some of these string rewrite rules turn out to be reversible. What do I mean? I mean that you can really run the thing backwards. So here's a really simple example of a rule which is often reversible. The rule just says, replace every red block with 2 red blocks. And here's an illustration of this system evolving over the first 4 time steps. So we have 1 red block, then 2, then 4, then 8. So how do we make this system run in reverse? Well, it's really very simple. All we do is turn the rewrite rule upside down. So now our rule says, replace every pair of red blocks with a single red block. And of course we if we start with 8 red blocks, then we get 4, then we get 2, then we get 1. So this is the system running backwards. So certain aspects of this system here on the left are reversible. However, I wouldn't say that the system is completely reversible, because, for example, if you start with a single red block, there's actually nothing which can generate a single red block under this rule here, and so there's no prior string which would generate this. And also, if you took a red block as the initial condition in this kind of inverted rule, that's actually a fixed point in the inverted rule. So this system's not reversible over all different initial conditions. However, I was able to isolate a class of these rules which are reversible for quite a large number of different initial conditions. And this is actually a fairly significant thing, as I want to talk about. So let me just say something about these systems in general. So in general, these kind of systems are defined firstly by a set of kind of domain strings, a set of strings which we put at the top of the rules. They're the things that get rewritten. And we actually need to have an important feature for those things in order to have a well-defined rewrite system. Well, we need to have the system so that the domain strings, like here we have red, blue, blue, etc. We have to have that is a prefix-free set. What's a prefix-free set? A prefix-free set is a set of strings such that no string is a prefix of another one. What do we mean by a prefix? Well, for example, cat is a prefix of catfish. A prefix is a string which comes at the beginning of another string. Okay? So I know that's quite a lot of terminology to swallow. Basically, all I'm saying is that we can't have two strings in the kind of domain of our rule, which both such that the start of one is equal to another. Because if we had a situation like that, it would be unclear which rewrite rule we should apply. Okay? So now you know this condition which is necessary for us to have a well-defined rewrite system. I can tell you about what kind of rules are reversible. Basically, the systems are reversible when the kind of range strings, the strings at the bottom of the rule, the things that stuff gets mapped into, when the set of those is a prefix-free set. We need to have that to be true. So we need to have that these strings at the bottom form a prefix-free set as well. And the reason is that we want it so that when we turn our rule upside down, it's also a well-defined system. And in fact, for the thing to be reversible, we need another condition as well. We need that for any string we're going to encounter, we need that thing's going to have a prefix in the equal to one of the strings in the range. Okay, so that just says that for any string we can do a well-defined rewrite of it. Anyway, you should be able to figure out the details of when a string is reversible just by looking at it, really. So I just want to show you a few different kinds of reversible string rewrite systems. Okay, so here's a fairly simple one. In this reversible system, the number of blocks within the string doesn't change during the evolution. And so that means that the system has to be periodic, okay? And it's quite interesting because when you run the system forwards, essentially you end up going clockwise around this cycle. And then if you want to run the system backwards, all you have to do is turn the rules upside down, and you essentially go the opposite way around this cycle because you run the system in reverse. You might be curious as to why I've insisted that there are green blocks along the right of this rule. And this is really a kind of artificial construction which I came up with to stop information being lost from the system at the right hand side. Of course, preservation of information is necessary to have the rule as reversible. You should have a look at the paper if you want to see a more thorough discussion of how exactly you can find reversible rules. Suffice to say that there is a large number of them and they occur very naturally. So I want to show you a few things about some of these reversible rules because they have some really very interesting features. This is a reversible string rewrite rule which only has, it has two colours plus this green, which essentially just then acts as a kind of borderline. So essentially this is really a kind of two-colour reversible system. And this is the thing running for a few time steps. But what's interesting is that we can actually run this system forwards in time and backwards in time as long as we like, and the system's completely reversible. And what's more interesting is what happens if we run this system backwards in time. You see here I'm showing you how the system runs from this initial condition, but this system's completely reversible, and so we can also run it backwards. And when we run it backwards, we see this kind of space-time pattern. And I think this is something really quite interesting, because what we're seeing here is that if we start with this initial condition here, then the string kind of crushes down and crushes down and crushes down until it gets to this point here, and then suddenly something changes within the system and we get this new kind of string grow out, which really looks quite different. And so I think there are some theories of physics, about cosmology, which say that the way the universe evolves is that the whole universe kind of, as well as having a big bang where the universe starts, eventually the universe goes into a kind of big crunch where everything gets crushed down to a point, and then we have another big bang. Well, this system seems to have some kind of behaviour like that. But what starts to get really interesting is when one looks at reversible rules which have more complicated kinds of dynamics. If one looks at reversible rules with three active colours, one can see some really very interesting kinds of phenomena. I mean, look at this system shown here. I mean, it looks like the system's running in quite a regular way for the first few time steps, but the string is getting smaller and smaller in a linear way. And then suddenly, when the string is at its smallest possible point, the behaviour mode seems to change, and we get this immensely complicated kind of pattern being generated, which seems to grow exponentially. So it's really quite remarkable that this very simple rule can have these two different modes. But what's even more amazing is that this rule is completely reversible. You see, what that means is that the same amount of information is contained within this little string as this great big complicated string as this kind of regular looking string here. And so these sorts of reversible rules, particularly the ones with complex behaviour, I think are pretty interesting from a kind of information theoretic point of view. I think that these kind of systems can also teach one something about physics. I mean, Stephen Wolfram comments on this kind of thing in A New Kind of Science when he talks about reversible cellular automata. You see, the thing is that there's actually a lot of different, very simple reversible programs, and there really doesn't seem to be anything to prevent these reversible systems from generating significant apparent complexity from very simple initial conditions. I mean, just look at this rule here. This is reversible, but if we start with this as our initial condition, just a blue and a yellow block, we can see that the pattern gets immensely more complicated, and yet this rule is reversible. Okay? And so, in a way, this kind of picture really includes the same kind of apparent paradox, in quotes, as is supposed to occur in fundamental physics. This paradox known as the arrow of time. So let me just explain this paradox, in quotes. Basically, the thing about the arrow of time is that on a small scale, at least, on a small scale, physics appears to be reversible. I mean, if you watch a video of a load of molecules bouncing around, if you watch that video in reverse, it would look pretty similar. So the laws of physics on a small scale are supposed to be reversible, and yet Boltzmann proved that the amount of entropy in the system, basically the amount of disorder in a thermodynamic system, increases with time. And so that means there's a kind of arrow to time, there's a kind of irreversible aspect to the evolution of physical systems, and yet the laws of physics should make the system reversible. So that's supposed to be a paradox, but if we look at a system like this, we can see that really that's not so much of a paradox. I mean, we've got the same kind of thing occurring here, but it doesn't seem quite so paradoxical. I mean, this system is completely reversible, and yet it seems capable of starting with this simple initial condition and then making things look a lot more complicated. And so here we just see that well, for a start, from an information theoretic point of view, the generation of complexity is really a bit of an illusion, because speaking information theoretically, every row of this system contains no more information than the initial condition plus the rules and the amount of time it takes to run. So in an information theoretic point of view, this system's not really getting any more complicated with time. That's why it's reversible. But it looks like it's getting more complicated with time. And so it looks like the kind of entropy of this system's increasing, but in a way that's a kind of illusion which is due to the limitations of our visual systems and analysis techniques. Also, you can make the arrow of time thing look really silly if you just think about what happens when you run this system backwards. Because, of course, this system is reversible when you run it backwards as well. And then you see the thing actually become more ordered as time goes on. And, it doesn't really make any difference if you run it forwards or backwards. So, this kind of makes the apparent paradox of the arrow of time seem less paradoxical and more kind of commonplace within the behaviour of simple programs. You can see more in Stephen Wolfram's book, A New Kind of Science. He really discusses these issues quite a lot. Okay then, so I think one can learn quite a few other things from these reversible rules. They have lots of different kinds of behaviour. Many of them produce these kind of hourglass-shaped space-time plots, similar to the ones which I've shown. And some of these have this interesting feature that there seems to be some kind of, like a phase transition, somewhere where the pattern sort of goes from being very orderly to very disorderly, or vice versa. And this sometimes seems to happen at this place where the pattern is as compressed as it ever gets. And there are also these interesting patterns where the number of blocks remains constant, but the system is reversible. So I think there are some applications to these reversible systems. One kind of obvious, albeit primitive application would be cryptography, because of course the amount of information in these systems is preserved. And another important feature is that you can put an orderly string in at the top, something like a message, and if the system has complex behaviour, then it can be incredibly difficult for somebody to decode the message unless they know which rule you used. Indeed, if you use something like a computationally universal reversible string rewrite system, then it can be a very, very difficult job for somebody to be able to reverse that kind of procedure of running the thing. So this is the basic idea behind this, as I say, rather primitive cryptography scheme. You write your initial message and you pick a reversible rule, which, hopefully one that generates complex behavior, and you just run use this rule and run the message on it. And you run it for a few time steps until the output looks quite complicated, and then you have an encrypted version of your initial information. So this diagram kind of illustrates it. And as an encryption key, all you have to do is tell the receiver who you want to communicate this encoded message to. You need to tell them which rule you used and how long you ran it for. And given that information, it's very easy for the receiver to decode this message. I mean, all they have to do is turn the rewrite rule upside down and run it sort of backwards for the amount of time that you ran the thing forwards for. Well, this is a fairly primitive method of cryptography, but I mean it is one application of these systems which stands out since they can generate such complex behavior of relative ease. I mean, in practice, this might not be such a good encryption technique because, for one thing, you'd probably need to have quite a large rule here in order to make sure that some kind of eavesdropper isn't going to detect the rule by, using a kind of brute force search. Anyway, another, I think, more interesting kind of potential application, or at least a theoretical kind of thing to look at for these kind of reversible systems, is compression. Because, of course, these string rewrite systems do have this property that these reversible systems do have this property that the amount of information is preserved with every update. And this is really quite surprising, I think. I mean, it really says that, the amount of information in this evolution process is not changing. No information has been created or lost. You can run the system forwards and backwards for as long as you like. And so this obviously provides a compression scheme. If we have some initial data and we want to compress it, all we have to do is run it under a reversible rule. And if the reversible rule we choose has the right kind of form, if it makes the input string get smaller, then we're really achieving compression there. Because, of course, we could just turn the rule upside down and run the thing backwards and recover our initial data. And so this is a form of lossless data compression. Here's an example. Say we want to compress this data here. It turns out that if we use this particular rule, we can just evolve this data under this rule until the data becomes very compressed, and then we can say that this is the most compressed data that we can get. And then if we want to, so all we need to do then, if we want to get a sort of a proper representation of this compressed data, is we need to record which rule we used and how long we ran it for, and what's this kind of small string which we were able to crush our initial data down into. And then, of course, if we want to recover our initial data, similarly to the cryptography case, all we have to do is run this rule for the appropriate amount of time under the inverted rule, and we recover our initial data. So this gives us a scheme for compressing things. There are a couple of sort of obstacles to this scheme. Firstly, of course, not every string rewrite rule is going to be useful for compression. There are some results about compression, and basically it's a very hard problem to find a rule or a system which can compress a sort of generic piece of data, because basically when you compress a piece of data, you have to exploit some kind of patterns that there are within that system. And of course, there's a hell of a lot of different patterns, and some kind of data can just about be uncompressible, because if your data was generated completely randomly, say, then it probably won't have a pattern in it to be exploited. So that's one thing. And what that means is that obviously there's no sort of magic string rewrite rule that can be used to compress anything. Another thing is a bit more of a subtle point, and that is that it can actually be very difficult to, even if you have the right rule, it can actually be quite difficult to use it to compress a piece of data in the best possible way. I mean, for example, look at this system here. When we evolve our inputs, I mean, it looks like we're getting this kind of hourglass-shaped space-time plot. And if we just have a procedure that we're going to stop our compression process or our evolution process when the string is at a local minimum size, as in when it decreased during this update and it increases during the next update, then we'll stop here because, you know, it's getting smaller, 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 and then it's starting getting bigger. Okay, let's stop. If we have that kind of primitive procedure, then of course we can compress the pattern a little bit. But if you want to find the absolute global minimum, if you want to be sure you've ran the rule for the appropriate amount of time to compress the string the best possible way, that can be quite a difficult problem, because we've already seen that some of these rules can have really quite highly unpredictable behaviour. In fact, in a new kind of science, Stephen Wolfram proposes this really radical principle called the principle of computational equivalence, which basically says that a lot of these systems which seem to have complex behaviour are going to have behaviour which is as complicated as any other computational system. And that means that this problem of using a rule in the best possible way to compress something is fundamentally difficult in general. Anyway, despite all of these troubles, I still think that these reversible string rewrite systems are quite useful for data compression. And I think that this is a really good thing, because compression is actually an amazingly important thing to be able to do. I mean, I think it was Gregory Chaitin who said that mathematics or science is basically just compression, basically just data compression. I mean, in science, you take a lot of different observations about the world, and you try and crush them all down into a few principles or theories, which can explain a heck of a lot of stuff. Similarly, in mathematics, you take a result which holds for many, many different objects, maybe an infinite number of not objects like the integers, and you kind of compress those observations down into a little theorem which really contains a lot of information. So understanding of science is basically compression, and so being able to do compression well is a very important thing. So basically, I think it's interesting to be able to see how we can do data compression using these kind of string rewrite rules. And I did develop a scheme for doing this. Basically, the idea is that, yes, if you have a particular rule, then there's only going to be some strings that you can compress using that rule. There's only going to be some kinds of patterns that your string rewrite rule is able to exploit. So the idea is just to choose a lot of different rules and then to test each one and see which one gives you the best kind of compression. So this is the idea. You input your data, you run many different kinds of reversible rules on your data, and you see which one of those compresses the data the most, and then you record the rule which does the best, how long you had to run it for, and what the compressed string is. And then, of course, you can recover your initial information. So I wanted to do some experiments with this, so I actually defined a set of 1,824 different reversible rules, and I tested them out on some different strings. For example, here, if we have this long binary string here, which I generated randomly, well, if you want to compress this, I tried to compress it under my system, and this is what I got. So this string is 67% of the length of the initial string. And here's the actual rule which compresses it. It compresses it down to here. And I've recorded as a prefix here the number of time steps I had to run the thing for and the rule I used. So it's quite easy to reverse this process. You just run this rule backwards for 2 time steps. So I think this kind of procedure, here I'm comparing it to, I'm comparing this compression scheme with the zip compression scheme used in Mathematica and also in WinRAR, and it seems to compress the data more in general. By the way, this x-axis here, this is given the percentage of ones in the initial binary string. So this is tested on binary strings of length 4,000. And the reason I checked it on strings which have different percentages of ones is because when there are almost no ones in the binary strings are almost completely filled with zeros, and so they're very orderly. And when they're very orderly, there's lots of compression that can be done because there's going to be lots of regularities in the data which can be exploited. But when you crank up this percentage of ones in the binary string up to 50%, then that means the string, since these are randomly generated, that means the string is effectively completely random. And you shouldn't expect any kind of compression scheme to be able to take advantage of that. And indeed, these cannot. So this plot shows that my method does outperform these sort of well-known methods. But I have to make a big concession here, and that is that my method takes ages to run. I mean, it takes like about 1,000 times longer than either of these two compression schemes employed by WinRAR or Mathematica. And I'm informed that, in fact, one can change these compression schemes to make them run longer. And I would find it rather doubtful that this very ad hoc scheme that I've come up with outperforms these commercial compression schemes if you allow these schemes to run for competitive timescales. Anyway, that doesn't mean that this idea of using these systems for compression should go in the dustbin, because I think that there's something fairly interesting about this kind of compression scheme. You see, the fact is that these systems are reversible. They can also generate complex dynamics. And that's fairly interesting because what compression is it is exploitation of certain patterns that there are in the data. And certain well-known compression mechanisms can exploit, they all exploit regularities, like if you have long runs of zeros in a binary string, a compression scheme can identify something like that and replace it with something smaller, something which takes up less disk space. And maybe if you have some kind of nested pattern, something like a fractal, then some very clever compression schemes can spot those kind of fractal patterns, and again they can compress them away. But you see, these kind of systems, they can actually compress away complex behaviour as well. And so if you have some data which was generated by one of these kind of simple programs, like a cellular automator or a string rewrite system, or even something like the prime numbers, if you have something like that, then it's going to look very complicated, but in fact it'll have a simple rule behind it. And using something like a compression scheme like this, which is capable of this kind of generation of pseudo-randomness, is good, because you can actually sometimes you can compress away these kind of seemingly irregular pieces of data, which are not really irregular at all. In other words, you can use these kind of systems to detect, sometimes at least, when a complicated pattern was actually generated by a simple rule. And you see, this could be quite a useful thing to be able to do. I mean, imagine you have some data from some scientific experiments. You could use something like this and see if one of these string rewrite systems compressed that data. And if it did, then that would really teach you something fairly important about the data. It would teach you that there are certain kinds of regularities. And moreover, since this is a dynamical system, you can then do things like extrapolate. Because if you find one of these systems that generates your data, you could run the system for longer, and then you get a kind of extrapolation of that data. Or you can reverse the system. And basically you can see the entire evolution process which generates what you're interested in. And so basically, I think reversible simple programs with complex behaviour can have a fairly important effect, and probably will have in the future, on the way people do analysis of data. Anyway, so that's pretty much the end of my presentation. I've tried to give you an illustration of what kinds of things these simple rewrite systems can do, and what kinds of applications they have. In particular, I've talked about the arithmetic, the reversibility, and also some applications of reversibility to cryptography and data compression. As usual, I really think we're just scratching the surface here. I mean, it's amazing how many fascinating complex behavior how much fascinating complex behavior can be generated by really simple programs. And by doing this kind of mining approach of just searching through and looking at what kinds of behavior these really simple programs can do, we can find all kinds of fascinating things. And I think the challenge is not finding systems of significant interest. There's loads and loads of interesting systems out there. I think the real challenge now is matching these systems with decent applications. We need to sit down and think about what kinds of things we can actually achieve with these systems, because they are useful for certain things. And I think some amazing technologies are going to come from looking at these kind of simple programs and what they do. But I think it's very challenging to actually identify what kinds of problems you can solve with these systems.